Hey all dear students, this is Prajesh Chaudhary, your Quantum Guru. In this video, I'll take two questions of thermodynamics related to efficiency of a thermodynamic cycle, one from Pathfinder and one from Irodov. First, I'll take question from Irodov, and that is a question number 116 from the second part of the book, that is the thermodynamics, heat and thermodynamics. So the question states, an ideal gas goes through the cycle consisting of alternative isothermal and adiabatic curves. So you can see that this is isotherm, this is isotherm, this is isotherm, and these are the adiabat. So we have 6 parts of a cycle, 3 isothermal and 3 adiabatic. The isothermal processes proceed at the temperature T1, T2 and T3. Find the efficiency of such a cycle if in each isothermal expansion the gas volume increases in the same proportion. So this part is the isothermal expansion. This part is also isothermal expansion. So in this part, volume expansion ratio is the same. That is what given is. So we have to find the overall efficiency of this cycle. So once again, this is my diagram. So T1, there's the dark yellow color are the isotherm and the blue color are the adiabat. And I have shown there thermodynamic states of these points P1 V1, P2 V2, P3 V3, P4 V4, P5 V5 and P6 V6. So this is isotherm, this is isotherm, this is isotherm, this is isothermal expansion, that is isothermal compression, this is adiabatic expansion, this is adiabatic expansion, and that is adiabatic compression. And the volume expansion ratio for the two parts which are in which there is a thermal expansion, isothermal expansion, the volume expansion ratio are the same. So for this part, the volume expansion ratio is V2 by V1, and on this part the volume expansion ratio is V4 by V3, and they are same. So I can write that ratio to be same and that ratio to be say K. So V2 by V1 is equal to V4 by V3, and that is suppose say K. I want to apply the adiabatic equation. That equation is T into V power gamma minus 1 is equal to constant. So that I want to apply TV power gamma minus 1 is equal to constant. Suppose I want to apply first for this adiabat at this point and this point. So at this point temperature is T1 and the volume is V2, and at this point temperature is T2 and volume is V3. So T1 V2 power gamma minus 1 is equal to T2 V3 power gamma minus 1. Alright, so what you can write? You can write now V3 by V2. So V3 by V2, just simplify that thing. We'll get T1 by T2 power 1 upon gamma minus 1. So here this is the final volume, this is the initial volume for this adiabatic expansion, and this is the initial temperature and this is the final temperature, and whole power 1 upon gamma minus 1. So same thing if I can apply for this. So final volume by initial volume, final volume by initial volume is equal to initial temperature by final temperature power 1 upon gamma minus 1. Same thing, rather than the final volume, initial volume, you can say the higher volume, greater volume upon lesser volume is equal to greater temperature upon lesser temperature power 1 upon gamma minus 1. Similarly here, greater volume by lesser volume, V6 by V1 is equal to greater temperature upon lesser temperature power gamma minus 1. So this is what we have obtained. So I am interested in this V5 by V6 I will be needing later. So V5 by V6, you can see this equation, there is V5, there is a V6, you just divide this equation by this equation. So you will get already I will do that thing. So whatever we obtained I have just put into this page. So I am interested in V5 by V6. So V5 is here, V6 here. So divide this equation by this equation. So we'll get V5 by V6, V5 by V4 divided by V6 by V4, V1. And here this T3 and T3 part will get cancelled. So we will get T2 by T1 power 1 upon gamma minus 1. Just rearrange this thing. So V5 by V6, and that will go to that side. It will make V4 by V1 into T2 by T1 power 1 by gamma minus 1. Now see here. Here you can see that V4 is equal to V3 into K. And there is a V1. V1 is equal to V2 by K. So if I put that, V4 is equal to KV3 and V1 is equal to V2 by K. So this denominator K will come into the numerator. That will make K square, and K square V3 by V2 into T2 by T1 power 1 by gamma minus 1. And see this V3 by V2 is equal to T1 by T2 power 1 minus gamma 1, and this is T2 by T1 power 1 minus gamma minus 1. Their product will become 1. So we will get V5 by V6 equal to K square. So the one very good result is that if the volume expansion ratio here is K, volume expansion here is K, so volume compression ratio here is a K square. That is also a good result that can be used. And now we can proceed to find the efficiency. So this is what we opt in an isothermal process, delta U 0. So Q is equal to W. And for this part, you can see this part, this is isothermal process. Whatever is the work, that is delta U 0. So the only thing here we can see that the work done is positive because volume is expanded. So Q is positive. So in this part, heat enters to the system, and same thing happens here. Suppose heat entered into the system, here is Q3. On this part there is a compression, so volume is decreases, so work done is negative, so Q is negative. If the Q is negative, mean the heat is rejected. Suppose the magnitude of the rejected heat is Q3, and on this part, these are adiabat, so no heat enters or leaves. So Q is 0 there. And now Q1, for this part, Q1 is obviously the W1 work done here, and this is isothermal process. In isothermal process, work done is equal to nRT ln final volume upon initial volume. So from here to here, temperature is T1 and the volume expansion ratio is K. So Q1 on this part is equal to nRT1 ln K. Similarly here, this is isotherm at temperature T2, volume expansion ratio is also K. So here Q2 is equal to nRT2 ln K. And in this part, it is isotherm or at temperature T3. So Q3 would be nRT3, and this V5 by V6 is equal to this V5 by V6 is equal to K square. So if I write Q3 with sign, that will be nRT3 ln V6 by V5, but because I have to write the magnitude of Q3, so that Q3 magnitude would be nRT3 ln V5 by V6, and V5 by V6 is K square, so that would be nRT3 ln K square. So that will become 2 nRT3 ln K. And now we've got all those things here. Now efficiency of a cycle is equal to 1 minus sigma Q minus upon sigma Q plus. What is sigma Q minus? Sigma Q minus is the sum of all heats that are total heat rejected in the cycle, and sigma Q plus is the sum of total heat enters into the system in a cycle. So the heat entered into the system are Q1 and Q3, and heat rejected into the system for this cycle is Q3. So sigma Q minus is equal to Q3 and sigma Q plus is Q1 plus Q2. So that would be 1 minus Q3 upon Q1 plus Q2, and just put the value of this Q1, Q2, Q3, and RT will get cancelled from each. So we will get sigma is equal to eta is equal to 1 minus 2 T3 upon T1 plus T2. So that would be our answer. And now I have another good question of Pathfinder from thermal physics chapter. It's build up your understanding, question number 40. In this question also, that is related to efficiency. So here that is a PV diagram is drawn. This is the indicator diagram. This is cycle 1 2 3 1, that is one cycle. This consists of a straight line, and this 2 3 is a adiabat, 3 1 is isotherm. And there is another cyclic process 1 3 4 1, 1 3 4 1, and this consists of this isotherm. This isotherm is common to both the cycle. This isotherm, this is isobar, and this again is an adiabat. Efficiency of this cycle 1 2 3 1 is eta 1, and efficiency of the cycle 1 3 4 1 is eta 2. So we have to find the overall efficiency of the cycle 1 2 3 4 1. Okay, so this is the diagram. The same thing here. This is straight line path. This is adiabat, 2 3 is adiabat, 4 1 is adiabat, and the common line is isotherm. And efficiency of this cycle 1 2 3 1 was given to be eta 1, and efficiency on this cycle is eta 2, and we have to find the overall efficiency of the cycle in terms of eta 1 and eta 2. Okay, so we just repeated that. I want to repeat that the efficiency of a cycle is 1 minus sigma q minus upon sigma q plus. Sigma q minus means the total heat rejected in a cycle, and sigma q plus is total heat entered. So for this cycle, this is obviously adiabat, no heat will enter or leave. This is some process. You can see that this is an isotherm, or don't see isotherm. There is some value of P and V here, and there would be some value of P and V here. The P at 2 is more than P at 1, and V at 2 is also more at V at 1. PV is equal to nRT. So a point where PV is more, temperature is more. So definitely temperature as 2 is greater than temperature at 1. So from 1 to 2, temperature increases, mean delta U is positive, and obviously volume has increased, so work done is also positive. So in this part, Q is positive, mean heat is entered into the system, and suppose that entered heat is Q1. In this part, no heat enters or leaves, Q is 0. This is isotherm, so delta U is 0, temperature change is 0, delta U is 0, and there is a decrease in the volume. So work done is negative, so it means the Q is also negative. Q is equal to W plus delta U. So Q is also negative. It means the heat will be rejected by the system, and that rejected heat is Q2. So efficiency of this cycle eta 1 is equal to 1 minus Q2 by Q1. That is eta 1. So I can rearrange that. Q2 by Q1 is equal to 1 minus eta 1. And now for this cycle 1 3 4 1. If from 3 to 1 heat is rejected, so obviously from 1 to 3, that is the just direction is changed, so heat would enter. So from 1 to 3, heat entered is Q2. Heat entered is Q2. 3 to 4. 3 to 4 again, this is isotherm, and at this point temperature would be at 4 temperature is less than compared to 3, because that is a adiabatic compression. So delta U is negative from 3 to 4, and volume also decreases, so work done is also negative. So in 3 to 4, Q is negative, so it means the heat is rejected by the system, and that magnitude is suppose say Q3. So that is a Q3 is the heat rejected from 3 to 4. 4 to 1 is adiabat, no heat enters, no heat leaves. So in this cycle, entered heat is Q2 and the rejected heat is Q3. So efficiency would be 1 minus Q3 by Q2. And rearrange that. So q3 by q2 would be 1 minus eta 2, and multiply these two. If you multiply these two, q2 and q2 would be cancelled. We'll get q3 by q1 is equal to 1 minus eta 1 into 1 minus eta 2. And now look at this overall process, 1 2 3 4. So this is adiabat, this is adiabat. So on this part q1 heat was entered, and on this part q3 heat was rejected. So the overall efficiency of this cycle 1 2 3 4 1 would be 1 minus q3 by q1. And q3 by q1 we obtained 1 minus eta 1 into 1 minus eta 2. So the overall efficiency is 1 minus eta 1 minus into 1 minus eta 2, and just simplify that thing. We will get overall efficiency to be eta 1 plus eta 2 minus eta 1 eta 2. And now see that we did not require what type of process is this. So even if this process would be something like that, still my answer would not change, or this process would be something like that, still my process would not have changed. So here these two processes are not important. Important thing is that this is adiabat, and in between there is isotherm. We will still get the same result. Thank you.